Good morning, everyone. Everyone doing all right? Any story from the weekend that you may want to share? No, not much. I think it wasn't the weather was pretty good, right? Lisa, that was very nice. All right. Well, I hope you had fun, and then you're ready to work in another homework if you haven't finished the first one. The first one was sort of easy and short. The next one is going to take you a little bit more work. Okay, so let's continue talking about geomechanics and about stress. We are in the week of January 27, and we're going to finish with lithostatic stress, or vertical stress is the same thing. We're going to talk about pore pressure, and we have one homework to finish for next week. So if you remember from last class, we were talking about total vertical stress, and that is the stress that we get from adding all the weight of the rock on top of whatever or wherever we are interested in. And this is a result just of gravity, and the deeper you go, the higher this stress is going to be. This value that we have calculated of vertical stress, and we did these calculations onshore and offshore, that's literally how much pressure you would need to lift the ground up vertically. So for example, let's go to our last example, this one offshore, and here we calculated that the vertical stress was about 8,000 psi at this depth of 9,000 feet. 8,000 psi. That's what we got. So again, if you wanted to lift the ground up with a hydraulic jack, you will have to put about 8,000 psi on that jack in order to lift the ground. So before we go into more accurate calculations, just to have an idea about pressures and stresses, do you know what is the pressure in the tires of your car? Anyone? Yes. A little bit less, like 30, 40. It depends on your car. It depends on the size of the wheel. But let's say 50 psi. Well, here we're talking about 8,000 psi. Do you know any other device that you may use in an appliance or something like that with a higher pressure? Like for example, in the bicycle, sometimes you can go to 80 psi, 90 psi, because those are a little bit smaller and they require higher pressure. Any suggestion? Okay, so what about a propane tank? How much is the pressure there? Do you know? It depends on the volume, or depends on the size of the tank too. The smaller the tank, usually higher the pressure you can get to, and it can go usually to hundreds of psi. Sometimes it can go even to 1,000. Some of the bottles of compressed gas that we use in the laboratory, and then you use like people from welding and things like that, those get to probably 1,000 psi, some others a few more. What's the name of those water hydrojets they use to wash your car? A pressure washer that goes actually very high. It goes up to 2,000 psi. So that pressure is pretty high. Those pumps are very good. Well, but here still we're talking about 7,000 psi, and that's quite a bit. Pumps that are used for hydraulic fracturing, usually they get to 10,000 psi. So it's more or less in the order of the pressures that we're interested in. We'll see later how to convert that surface pressure to whatever we need on the subsurface. But here, just I wanted to make the point that we're talking about very high stresses. Oh, and one more example. In the laboratory, the cells that you're going to use them up to more or less 500 psi of pressure. And you're going to apply a few thousand psi of stress, of vertical stress. That's what you're going to need in order to break the rocks. Okay, so we saw how to compute this stress whenever we have a constant mass density. But that's not the case on real life. In real life, the density of rock varies with depth. And here I have one example. This is an example in which we have depth as a function of, density as a function of depth. This comes from a well log. It's actually a density log. And you can see how density increases from more or less about 2 grams per centimeter cube to 2.5 grams per centimeter cube as you go deeper. If you want to calculate the vertical stress with this data, then it's not going to be as easy as just multiplying depth times density. You have to do something else. And that something else is what we're going to see right now. And in theory, it would be to apply an integral of the density times g as a function of depth. But basically this integral is what it's saying is just getting the weight of each layer, each particular layer, and adding that up as a function of depth. In practice, we're not going to use this integral, but we're going to do a numerical integration of that integral. And the numerical version of this integral is going to be this equation, in which the stress is just going to be the weight of each of the layers on top. So you can see, for example, here, this is the summation of all the layers from layer 1 to the layer that you are interested in. The density of the layer at that depth, the gravity constant times the thickness of that layer. So each layer has its thickness, its density. You add up all of them and you get the value of vertical stress. And it's not too complicated. So let's see an example. How many of you have your computer here right now? 1, 2, about half. Okay. So you don't really need your computer today, but please bring your computer on Thursday so we can work on this second problem, which involves files which are a few thousand rows long. So you cannot do it manually. You're going to need your computer. And it's actually a well log file. But for now, let's see how we apply this equation to a simpler problem, and it is this one. It's actually part of problem number 3 of the homework, and what we're going to do is we're going to calculate vertical stress as a function of depth, considering that density is not a constant but it varies. Okay? So let me get started with this. I'm just going to copy this data. And there is one more column here about shale porosity. Don't worry about that. We're going to talk about that later on. But let's see how we do the calculation of vertical stress. Okay, so that's the data, and let me make this a little bit bigger. This is depth, and let me check the units. It was meters and kilograms per meter cube. And this is mass density, bulk density. So if you want to use your computer now and just start working with this, just feel free to do that. If you don't have your computer, I encourage you to do it manually, at least the first rows, and then later you'll see that when you do it in your computer, it's going to be super easy. The most important thing from here is that I want you to figure out this issue of the densities and the units to get it right. Okay, so all right, so I have depth, density, and porosity. The first thing I want to do is I want to calculate what is going to be vertical stress. And total vertical stress, we call that one SV. And just for now, let's do it in units of the international system, that is going to be pascals. So we're not going to do any unit conversion, okay? All right, from the formula, SV is going to be equal to the density of the layer times the constant of gravity times depth. At the depth of 0, SV has to be 0. Okay, well, the next one gets a little bit more interesting. Now I have to add, at the 100 meters, I have to add everything which is on top of those 100 meters. And what I'm going to do here is, this data, we have data every 100 meters. So what I'm going to do is, I'm going to use an average of the density. So instead of using the density of that layer, since I have data in those 2 points, I'm going to use this density, that density. I'll take an average of that, and I'll use that density as the average density of the layer. And this is the same as if you remember doing the trapezoidal rule for integration. Is the area of that trapezoid whenever the density is not constant. And I'm going to do the same thing, multiply times gravity, and then multiply now times depth. But here is the one thing which is going to be different too. You remember from the equation that we have a delta Z, and then we add all the weights. So here also I'm going to have to multiply the density of that layer times the thickness of that layer. And the thickness of that layer is going to be 100 minus whatever is on top. So this is the number that I get at the 100 meters. All right, before I do the unit conversion, just more or less from the values that we talked about before, what is the vertical stress or the pressure that you would expect at 100 meters of depth? Those are numbers I want you to remember, because they're going to help you a lot to see if your numbers they make sense or not. Hydrostatic gradient was how much? Let's say in psi per foot. 0.44, right? And what about in metric units? It was more or less an easy number. I'll remind you that it was 10 MPa per kilometer. So if we have 100 meters, that's a tenth of a kilometer. So we should expect more or less 1 MPa, 1 megapascal. And I don't know if you can see there, but that's close to 1 million. So when I do here SV, let me convert it to megapascals, what do I have to do in order to convert a pascal to a megapascal? Seems like a silly question, but sometimes I get this in exams. What is a conversion from a pascal to a megapascal? What? Yes, 10 to the negative 6. So you have to divide it by 1 million, okay? So of course that's going to be 0, but I just want to apply the same everywhere. Oh, what do? I divide it, I had to multiply. Okay, you see it's close to 1 MPa because the density is close to 1,000 kilograms per meter cube. All right, so up to here, up to 500 meters, we have water. So let me put the shade on this that looks more or less like water. Below this, we have the rock. All right, so I did the first one. Can you work and tell me the second one? What is going to be the vertical stress at 200 meters? Okay, I'll let you work a little bit on that. As I told you, you can do this in paper 2. It's not too difficult. And let me know if you have any questions. Yeah.
I'm having a little trouble trying to find the values for the depth and voltage.
What do you mean specifically?
Like where on the on your website, you can find those values.
Oh, that's in section 2.4. This is the problem of the homework. So you can copy that table and paste it in Excel, and you should be ready to go. So let me make a zoom here. So notice that it's the same simple equation that we have been using, but now we're just calculating the thickness of each layer. There is a little trick though for the next layer. What?
You just drag it down.
That's where the trick is. There is something I didn't put in there, but I like that you try to figure out on your own. So my question is, what is going to be SV at a depth of 200 meters? Okay? And if you have the answer, please let me know. I'll be glad to give you some extra points for that. Yeah. 2 megapascals. And let me just drag this equation to the next value. So I get 1, but what am I missing here? And this is something that it's also like kind of a common mistake. No, it's okay. I'm calculating the thickness. You have to add the one above, right? Because this is a summation. What I'm doing right now, I'm just calculating whatever is in that layer. But in order to get the value of stress at that depth, I need to add the one above. So once I do that, now I get 2 megapascals. And now I can drag it down to the very bottom, and then I get the value of stress. And let me do the same with this one and just change the number of significant digits. I always forget which one is this. Wait a minute. All right, yes, that one. I think that precision is enough, 2 decimals. So you see how clearly the vertical stress increases with depth. And let's make a plot about that. So here I'm going to use a scatter plot, and usually we make these plots so that in the x-axis we're going to have stress, and in the y-axis I'm going to have depth. And usually we want depth to go down, and so that's, let me complete this. I'm going to put some axis titles here. This is depth in meters. This is vertical stress, total vertical stress. In megapascals. For example, at the depth of 2 kilometers, if you remember, the stress gradient onshore was about 23 MPa per kilometer. So if we were onshore, we should have about 46. But we're not, in this case, onshore, we're offshore. That's why the value is lower. It's less than 40, which it makes sense. All right. So I hope that you could see clearly in this example how to calculate the stress with the metric units. Let's do it now with the field units. Yes?
Is the simple averaging of the bulk density a good assumption at the switch between water and rock, where it jumps from like 1031 and then 100? It's still good. It just average those two regularly.
At this point?
Yes.
So let me see. Up to this point, this is fine, right? In this one, we're averaging the depth of the water and the density of the water and the density of the rock. Probably you're right. This is not the most accurate assumption over here, but I think for the sake of this exercise, we're just going to leave it like that. You should also consider that next to the seafloor, the rock tends to be very light, and it has a very high porosity. So I think the error that we're doing in just applying this method, it's relatively small. But if you wanted to do it accurately, we actually have to do is, instead of working intervals of 100 meters, working much smaller intervals where you capture those densities a lot better, and this error will be a lot smaller. In fact, we are going to see that when we work with this actual example with the log file, I believe the data is every half foot. So it's very small. But that's a very good point. All right, so okay, that's with the metric units, okay? Let's do it now with the field units and using the method that I was telling you before. So I'm going to leave here one column empty, and I'm going to put here SV, and we're going to calculate this in PSI, and the equation is the same, okay? But now we have to use the gradient for in PSI per foot instead of the densities. All right, so let's go with the water. With the water, you remember we said the gradient was 0.44, right? But that was for a density of 1,000. So if we have a density higher than 1,000, we have to increase that proportionally to the density. So I'm just going to do the ratio of 125 divided 1,000. And then what I have to do now is I should multiply that times the depth, but now in feet. All right? So probably I should have, let me, this is wrong right now, okay? But I'm going to change it in a bit, because I'm going to add here one column where I'm going to do this conversion over here. So the depth is equal in meters, that divided 0.305, and that's the value. Let me fix this. Alright, so I have now depth in feet as well, and let me correct my formula. So this is the first value of SV. Of course it's 0, but I need that 0 so later I can modify my formula and add the previous value. And now I have to fix this to use the average density. Let me see if that looks alright. Let me know if you find any problem with that. And I need to take the difference now. Let me see what I did wrong. Okay. Oh, I'm missing the previous value. Okay, I guess this should be fine. Let me see when we get to, so for a depth of 1600, that times 44 should be less than 800, about 700. So I think it makes sense. And let me see if I found any mistake over here. Just to double check it, so I'm gonna put this in one color because it's one method. The other one is another one. Here I'm just going to do a simple unit conversion. Okay, well that's fairly close. There is an error of a few percent that probably aren't due to one of the round numbers I'm using over here. But you can see it gets very close. So what I did now in this second case was to calculate directly vertical stress, but now with the assumption that we were doing about the gradients. The gradients are proportional to the density. And for a gradient of 0.44, that corresponds to a density of about 1,000. All right, so work on that for a moment and let me know if you get the same values or similar values. And in the meantime, I'm just going to repeat this plot, but I'm going to do it now in field units. Let me see if I fix this. 247. No, that's going to be even smaller. Okay, and see here also you can see a little bit more clearly that for a depth of 7,000 feet more or less, we should get a value of stress which is lower than that, and we actually get about 6,500. I hope you notice the kink here in the curve, right? That's when we pass from the water to the rock, and that's why the vertical stress increases more deeply, more steeply. Okay, well, I'll let you a little bit to work on this. Again, this is part of the homework due next week, so you may want to do it as soon as you can. Let me know if you have any question, okay? Yes.
What's that right hand? Did you just convert from here? And
Yes, that's the only thing. I just did a conversion. I was actually thinking about that. And I tend to run sometimes too much, but it's let me double check this. Okay, now we're getting closer. One MPa is 145. I was right. 145 psi. So the only thing I did here was to multiply this times, let me fix it back to what it was. I multiplied times 145. I just wanted to compare these two. The one that I obtained using G, which is this one. So let me label this. And this one is using field units. Okay, let me try something else to be a little bit more precise. If I remember correctly, this is actually 433. Okay, now we're getting closer. And this is the exact same thing that you're going to do in the homework with the logging file. It's just that it's going to be a lot more data. So when you work on the logging file, you can do it in Excel. That's fine. I think it's a little bit more didactic to play with this and see that actually numbers make sense. But if you want to do it also in Python, that would be even better, and that would be a good training for you for the future to deal with these files. And if you're really pumped about coding in Python, you could even create some sort of function that gets any well logging file with the logging format, which is LAS, and calculate vertical stress out of there. And in the future, you just could use that. Just get any logging file, any deviation survey, and get vertical stress out of it. It's just a little bit of math, nothing else. All right. So, do you guys get the same numbers? So we can move on. And let me put here some extra points. All right. Okay, so what we have done now was we have used this formula in order to calculate vertical stress as a function of depth. On Thursday, when you all have your computers, we're going to do something else, something additional, and is that instead of using what we have used now is true vertical depth. What we're going to do on Thursday is to use a deviation survey from a wellbore in order to convert measured depth to true vertical depth and calculate vertical stress. The depths that you see in a typical well logging file, those are not true vertical depths, those are measured depth. And here you could have, for example, a wellbore that goes inclined or even goes horizontal, and even though measured depth increases, the vertical stress is not going to increase, right? So let me do this with an example over here. What I mean is, if you drill a wellbore and at some point you go with the lateral, the vertical stress is not going to increase as you go in the lateral. The vertical stress here, there, and there is going to be more or less the same, because the true vertical depth is not going to change. When you read the wellbore and you read the data from the wellbore, you will see that the measured depth, it increases a lot. It's always increasing. But that doesn't mean that the true vertical depth and the vertical stress is going to increase. All right. So then we're going to see this on Thursday, and you have the last problem of the homework is related to this as well. If you want to get started with that, so on Thursday probably there is just one minor thing that you want to fix. If you follow this link over here, it will take you to right here to a GitHub repository where I already have the files that you have to use. So here you have a well logging file. We'll talk about this on Thursday, typical well logging file. And in addition to that, you have a deviation survey, which tells you, as a function of measured depth, what is the true vertical depth of the wellbore and in which direction it goes on easting and northing. We'll talk a little bit more about that too. But you can get started with this if you want. All right, so let me come back over here. We'll see that later on. You're going to get something very similar to this. Notice that although this data is very regular, the vertical data at the end is a smooth curve because it's an integral, because it's a summation of everything. So it naturally averages everything which is on top. All right. We have finished with vertical stress. Remember, vertical stress, total vertical stress is the weight of everything on top. And this is going to be your best friend in geomechanics. Every problem that we work with, the first thing that you're going to have to calculate is total vertical stress. And also, I'm telling you this is your best friend because it's a value that for which we have the highest certainty and accuracy for calculation. We're going to see many other things right now, like pore pressure, horizontal stress, that we don't know, or we have to measure it in situ in order to get to know what they are, or we have to use some other methods which have some error in order to know what they are. But for vertical stress, it's relatively straightforward. You know density, you know depth, you add all the way above that, and that's it. So that's a value that we know very well, and it's going to be very useful for all the rest of the things that we're going to do now. Okay, the next thing that we're going to do now is to calculate pore pressure. And here you have an example of pore pressure. This is hydrostatic pore pressure. But we're going to calculate pore pressure, not hydrostatic pore pressure, which that one is very easy. You already know how to do 0.44 times depth, and that will give you more or less hydrostatic pore pressure. We're interested in cases in which pore pressure is not hydrostatic. And this happens in many basins, not everywhere, but happens in many basins, and it's also a function of depth. And this is critical for geomechanics, because if you remember, what I told you was a critical parameter was effective vertical stress. And effective vertical stress is the difference between total stress, total vertical stress, SV, and the pore pressure. Here this is the actual pore pressure. And if that one varies as a function of depth, that's going to change a lot many things. All right, before we get into detail about talking about pore pressure, I wanted to show you an example of a paper I was reading recently, which summarizes these trends of pore pressure. What you see in this plot is depth, pressure. Now we can read, and you can get to understand a little bit better these plots. This solid black line, that's total vertical stress, SV. You know how to calculate that one right now. Here in blue, you have hydrostatic pore pressure. And here in yellow, you have the fracture pressure, something that we're going to see later on, how we calculate. And here you have two other lines, which are pore pressures which are not hydrostatic. And this is a general trend that is observed in offshore. Gulf of Mexico, North Sea, you see that around a depth of 2 to 3 kilometers. Above that, pore pressure is hydrostatic, but below that, pore pressure is not hydrostatic anymore, and actually it starts to increase with depth. And that makes geomechanics a little bit more complicated for the reasons that we're going to see later on. But for now, I will just like that you remember that pore pressure in many places, especially offshore, is not hydrostatic. And usually you get to higher pore pressures than hydrostatic as you go deeper. And also that makes drilling more complicated, and also some other things like full reactivation more likely to happen, and it makes the rock weaker in general. And that's very important to consider, and that's something that we're going to work with later on a lot as well. Unconventionals usually are overpressured. The pressure is not hydrostatic. A good unconventional rock will have a pore pressure which will be quite higher than hydrostatic. And that also makes the completion easier and makes the recovery of oil and gas easier as well. So remember, pressure, pore pressure can be hydrostatic sometimes, but many times it's not. And if you assume a pore pressure as hydrostatic in a place where it's not, that's going to be a huge mistake. So let's see now then what are the reasons for the pore pressure to depart from the hydrostatic trend. All right, and this is one more example here in Gulf of Mexico. I'll talk about this overpressure parameter in a bit. First, just let's talk about what are the reasons why you could have a non-hydrostatic pore pressure. Okay, there are several reasons, and I'm going to go through the first ones very quickly, and then we'll talk about the main one. The first one is when you have a fluid that doesn't have the density of water. A hydrostatic gradient means that the pressure increases because of the density of water. If you have some other fluid, like for example natural gas under an anticline, because the gas doesn't have the same density of the water, inside the gas cap, the pressure of the gas is not going to increase hydrostatically with water density. It's going to increase with the gas density. And the difference between the gas and the water density, between the gas and the water pressure is going to be a function of the difference between the density of the fluids. The higher the density of the fluids, the higher the mismatch of pressure that you have at the top of this gas cap, or if it's filled with oil, that one will be with oil. This is the reason why if you're drilling a wellbore and you hit the top of the anticline with a very high gas column, what's going to happen? What are you going to get when you're drilling? I think I heard somebody say starts with K. A kick. You're going to get a kick, right? Because you're drilling with a given mud weight, which probably is enough to overcome the pressure of the given by the hydrostatic gradient. But as soon as you go through the shale, which is relatively impermeable, and you hit the reservoir with a high pressure, you're going to get a very high pressure that you're going to have to take in order for everything not to go worse, right? So this is the reason why you may have a pressure which is higher than hydrostatic. It is static because it's with the density of the fluid, but now it's another fluid, but it's higher than what you would expect with water. Here we have a schematic of some other reasons why the pressure also could not be hydrostatic. For example, if you have a basin that suddenly goes to an increase of temperature. The increase of temperature would make the fluids to expand. If those fluids cannot expand, they have to get a higher pressure in order to be in the same place. And because of that, you may also get, because of dilation, an increase of pore pressure. A similar thing happens with some chemical reactions, especially when you go deeper. It gets hotter, it gets higher pressure. There are some minerals that start to form that wouldn't form at surface, but they form at depth. And there are a particular type of clays, which are these smectite clays, that when you go from a transition from one type of clay, in this case morillonite, to this other type of clay, which is illite, in shallow conditions you have water between the clay, but when you go deeper and deeper, those two kind of like fuse together. They get very strong links between those with potassium ions, and they release that water, and that water that gets released also gets into the pore space, and if it cannot go anywhere, also increases the pressure in a formation. And the third one, which is also very common, is when you generate hydrocarbons. When you go through the oil and gas window and organic matter starts to break down, that organic matter that was in a solid state and was in a denser state, when it goes into gas or when it goes into an oil, it might go into a lower density phase, and that means that for the same amount of matter you'll need more volume. Again, if that volume cannot be accommodated, pressure is going to go up. And that's why source rocks, when hydrocarbons form, they start to break, and that's how hydrocarbons escape to the surface, because they get pressurized so much that the hydrocarbons, they just break through the rock and make it to seals. And some other times they don't, but we can go then and break the rock on our own and get the hydrocarbons from there. All right, so all of those are very important sources of overpressure, by which pressure could be higher than hydrostatic. You should know those. I might ask those in exam, but to the same level of discussion that we just did right now. The mechanism that I was telling you before in offshore conditions that makes pore pressure to be higher than hydrostatic is something which is called disequilibrium compaction. And let me explain what that is with a simple example, which is this example over here. Imagine that you have this container on the left filled with solids like spherical bits of some material, and that's also filled with water, right? You put a piston on top with a certain weight and you close the valve over here. What is going to be the pressure of the fluid inside the container? Can anyone tell me that? What? The weight and divided by? Divided by the area, right? By the area of the piston. So that's going to be the pressure. Let's neglect for a moment hydrostatic pressure, okay? Let's imagine that weight is quite heavy, so any increase of hydrostatic pressure is negligible. But I hope that you all see that if we close that valve and if the piston is not touching the solid spheres, the pressure of the fluid is just going to be whatever is applied by that weight. All right, so if we were to open now that valve and we let the piston go down a little bit until it touches the solid spheres, at the point that happens, the solid is going to start to take some of the weight, right? Because it's going to react. It's going to oppose deformation, and now the pressure in the fluid is not going to be the weight divided by the area anymore, because now also the solid is taking some of that load. Now the load is shared between the solid and between the fluid. And eventually, if we just let that sink, so that all the fluid that wants to get out gets out, at the end, in this case, all the weight is just going to be taken by the solid part and nothing by the fluid, because now all the load is just being opposed by the reaction of the solid. This exact same thing happens in nature, and the case in which the solid is taking most of the load and the pore pressure is not taking much or zero, it will be the case in which we have hydrostatic loading. Actually, if I were to draw here what will be the increase of pore pressure with depth, and now if I take into account the hydrostatic gradient, here it will be zero, but then it will increase with depth, right? And that will be the case of the hydrostatic pore pressure. But this case, it is not. We have a pressure which is higher in the fluid because the water didn't have the time to escape. And this is what happens in nature when we have overpressure. And this is something which is called, let me skip this for now, it's called disequilibrium compaction, and it happens when the rate of sedimentation is much higher than the rate at which the fluid can escape out of a sedimentary basin. So I don't think I have the right plot to do this, but I can do it. Here are my notes. So let me explain what's going on here. Have you guys gone to Galveston? Would you recommend anyone to go to the beach in Galveston? No? Yes? No? Why not? Why not? Why you wouldn't go to Galveston? It's muddy, right? That's the word I was looking for. It's muddy. Why is it muddy? It's muddy because we have rivers, we have the bayou there and all of that. They throw a lot of sediments on the water. Those sediments are composed by clay, silt, sand. The sand will tend to sink very quickly, but clay and silts, they will remain in the water. That's why it looks muddy. But it is also that same sediment that then goes further into the continental platform here and sediments into the seafloor, what eventually makes up these sedimentary layers that from which we extract oil and gas too. And those sediments are going to drop at a rate which is given by how it's the load of sediments that comes in the rivers, right? So when these sediments drop at a velocity which is faster than what the rock can release, then that's when we have overpressure. Let me you should think the rock as in a sponge. So if you have a sponge filled with water and you squeeze it, the fluids are going to come out from the sponge very quickly, right? That's because the sponge has a high permeability, and also, let's say water is it has a low viscosity. What about if you have the sponge filled with peanut butter? You think you will be able to squeeze it the same as filled with water? Probably not, right? Because peanut butter is going to be a lot more viscous. Well, with rocks, we have the same thing. If we squeeze a sand, which is filled with water, probably the water is going to come out very quickly. But if you try to squeeze a shale, because the shale has very tiny pores, it's going to take a very long time for that water to come out from the pores. And that's going to be a function of the permeability of the rock, the viscosity of the fluid, and also is going to be a function of the length of or the thickness of that formation. And that's what is going to tell you how fast pore pressure can go down as you squeeze something. And what it happens in these offshore environments is that if you add sediments very quickly so that vertical stress increases at a rate higher than what the pressure can be released, then you end up in a situation in which the pore pressure ends up being higher than what the hydrostatic trend should be. So here I could make a plot of vertical stress. Let's say this is depth. I'm going to draw what the pore pressure should look like. So pore pressure would increase more or less with the hydrostatic gradient. We said that usually in offshore conditions it continues for some depth, and then we don't know. This will be pore pressure. If we draw what is vertical stress is going to be the same as pore pressure at the seafloor, and at the seafloor is going to start to increase, and we know that this one is going to increase at the gradient higher than pore pressure. Well, what I'm telling you right here is that because the same case as the example we saw before, because the water cannot escape in these conditions, the water is going to get locked in the rock, and its pressure is going to be higher than hydrostatic because of that reason. And this is what we call a pore pressure departing from hydrostatic pore pressure, what we call overpressure. And the good news is that we can calculate that. And that's a method that we're going to see now in order to calculate that. And it's based on the concept that the rock didn't have the time to squeeze all the way as it would without overpressure, and we're going to see that reflected in the porosity of the rock. So before we go to that, let's do a schematic here about what we would expect. Let's say now this is porosity, and again this is depth. We just have rock starting at the seafloor, right? All right. What happens in general with the porosity of rocks as depth increases? The deeper we go, porosity should decrease, right? And why? Close, you're close, but compaction, right? But what is behind compaction? It's not pressure, and it's something that we have been talking about. Yes, but which one? No. This is going to, the force behind compaction is effective vertical stress. And if you remember, this was a difference between the total vertical stress and the pore pressure. So in this particular case, we can see that this effective vertical stress, when we get to the seafloor, is 0. That was a condition in which the octopus was able to get into the sand. But as you go deeper and deeper, the effective vertical stress increases. Whenever effective vertical stress increases, you should expect porosity. Let me draw porosity here again. Porosity should decrease, because the higher the stress on the rock, the vertical stress, the more forces you have grain to grain, and that's going to make the pore smaller. And if you were to continue on conditions in which the effective vertical stress increases, such as hydrostatic pore pressure, you would expect all the time this porosity to decrease. It's a little bit non-linear, so it's not just going to be in a straight line, but it's going to tend to a hydrostatic, to an asymptotic trend. But however, let me make this look a little bit more dashed. Okay, let me see if I can do this. Okay, this looks a little bit better. So this is what I would expect. But what happens in this condition is that vertical stress is not going down in this case, right? But in this particular case, with overpressure, effective vertical stress seems to even to be reducing. So the actual trend that you will see with porosity it will be this one. And this one will be what you would expect with pore pressure to be hydrostatic. Yeah. Say again?
Is it linear?
This line?
Yes.
No, it's not linear. This one? I mean, I just made it up, that one. But this one will depend exactly on this value. The good news is that we have an equation for this line. So if we have an equation for this line that you can measure in the laboratory, you can tell what is the porosity as a function of effective stress. And since you can have that equation, let me show an example over here. Can find it right now. Oh, here it is. This is the equation. This tells you that what is porosity as a function of a given effective vertical stress, and with this equation we can calculate effective vertical stress, and if you know effective vertical stress, then you can calculate what is the pore pressure. So this equation that I was telling you looks like this. And if you plot it, it looks like this. So if you know the porosity, which actually we know, how do we measure porosity in the field? With neutron porosity, with density porosity, with sonic porosity, you can measure porosity. If you measure porosity, knowing this, what are the parameters of this equation, you can get to know what is your value of sigma v. If you know what is sigma v, you know that this is equal to that. And if you know this one, which other one you know from this equation? This one, right? We said this one is relatively easy to calculate. And therefore, you can calculate your pore pressure. And this is what you have to do in the problem in the homework for next week. So if we come back where we started, here we have our profile of densities. We already calculated vertical stress, and with shale porosity and knowing the properties of this shale, here are the two parameters, you're going to be able to calculate what is the actual effective vertical stress that corresponds to that shale. And with that effective vertical stress, you can calculate pore pressure, and you can tell whether this is hydrostatic or not. And let me tell you the answer now. It's not going to be hydrostatic for the entire interval. There is going to be a point in which it's going to start to kick off to be different from hydrostatic, but you're going to pick up that from the anomaly in the shale porosity. The shale porosity, let's see if we can more or less see that in the numbers. You see that starts decreasing, but at some point it increases, and then it decreases a little bit. Well, somewhere over there you'll find that you have a overpressure because the shale porosity is higher than expected. All right, I'll see you on Thursday, guys. Remember to bring your computer so we work this problem about the well log.